Hello, ladies and gentlemen, and participants of KGI Conference 2020. My name is Chun. I'm from Graduate Institution of Architecture of National Jiao Tong University in Taiwan. And the topic I would like to present today is After Abstraction Before Figuration, exploring the potential development of phone retopology and evolution replication with three-dimensional point cloud model generation logic. The context of this research is derived from the book Digital Design Media. The book mentions that each pixel in the bitmap is independent and develops the concept of layers to manage the data of the three RGB color channels separately. So it is easy to extract the pixels whose color data is within a specific range through computer vision technique. So that pixel selections can be selected and added quickly without the mouse selection. While in the 3D CAD platform, constraint-based modeling has been developed, with which user can model quickly and simply by constraining geometric properties, such as the length of the lines and the rotation angle of the rectangles. However, due to the development history of CAD, the limitation to meet the requirements for manufacturing and the efficiency and cost of computer processing in the past, the geometric in 3D CAD are simplified to be displayed in the interface as solid object, which limits many geometric creative developments. Fortunately, in the 21st century, a new type of geometry appeared, called point cloud. A point cloud is a set of data points in space, and point is the purest and most primitive geometric element. In addition, the relation between the points in the point cloud is the same as the pixels in the image. Each point exists independently and does not affect each other, and a single point can store multiple dimensions of information at the same time. So we believe that point cloud can be used as the geometric design material. And in Durable Architectural Knowledge project, they developed a plugin called Volvox. It can quickly import point cloud into Grasshopper, so it solves the display performance problems of point cloud in 3D CAD platform. So we are challenging to develop a new modeling logic in the 3D CAD, breaking through the physical constraint of traditional modeling and the editing method, in which geometric material are oversimplified before being applied, using points the purest and the most primitive geometric material, without simplification of geometric data, to model evolution directly and find out more possibility and creative development of computer-aided design. And at the same time, we combine computer vision technology to change the role of colors in computer-aided design, from only for displaying materials to database that can drive design development. Finally, we also combine the common point cloud open source libraries such as PCL, Point3D, and XApp to enhance the accuracy of point cloud analysis and selection. So we divide this research process into four parts. Firstly, we attempt to explore efficient methods to obtain a 3D point cloud model from different form and different scales of objects. Secondly, we integrate Python open source point cloud libraries such as Open3D, Python PCL, and Grasshopper plugin Volvox to import and resample point cloud data. Thirdly, we transform point cloud from 3D world coordinates to 2D pixel coordinates for integrating computer vision techniques into point cloud processing. And finally, we use point set registrations and computer vision technique to improve the adjustment feasibility of 3D point cloud model in Rhino. Photogrammetry and 3D scanning are the two primary methods of reverse modeling from a real object. So in this slide, we show the result of these two different 3D reconstruction methods. And because a camera and photogrammetry software are usually less expensive and more easier to transport, so we propose a Grasshopper workflow for model reconstruction based on photogrammetry. The resample module, which is based on the moving these square functions in PCL, was used to estimate the normal vector of points and improve issues such as broken and rough surface caused by shadows or light refraction. Then we proposed the use of random sample consensus through the sample consensus modules in the PCL to remove outliers and noise near ground. Thus, the data obtained using photogrammetry can be regenerated without noise. Then, after resampling point cloud data, we indexed the point cloud and selected the number and location of necessary projection planes according to front and feature. Then we project point clouds onto multiple selected planes, and the shortest distance between each point and its projection points was considered as the depth data. So when two or more point clouds were projected in the same position, only the point with the smallest values in the depth data was selected to be projected onto the plane. And we use the module in OpenCV to establish depth image based on the depth data and the obtained projection result. Next, we convert depth image to range images according to the values in the alpha channel to ensure that the point selections and feature detections in next steps can occur without interference from different materials or surface. Finally, we index each pixel in the projections image and store RGB data sequentially in accordance with the image coordinate system. By this approach, we utilize the index relationship between the 3D point cloud and each of pixels to complete the point set registration process and minimize the data. After we complete the data index process, we try to import the results into Photoshop, created replacement materials, and featured special effect processing. Then the results were returned to the 3D model using the point set registration method. In this slide show the result of material replacement and special visual effect presentations of the point cloud model through the workflow we mentioned above. By this process, we hope that design concept can quickly simulated and visualized in Rhino Grasshopper, so that rational analysis and logic can be combined with perceptual design thinking and more innovative design results can be presented. And based on the above experience, we can also project all of the points in the 3D model onto the orthographic projection plane. Then selecting and marking the area of the projection image that we expect to be deleted with a black rectangle. Finally, we can remove all of selected points in accordance with the point set registration to prove that the 3D point cloud model can quickly and comprehensively select a specific area by using the selected index of pixels in the projections image. Except for the traditional 3D space information, the point cloud model is also endowed with highly accurate material information. Therefore, we choose to only preserve the points with the minimum depth values in the same pixel coordinates and attach a pattern with highly complex colors and shapes onto the projection image. Therefore, we can easily use the index relation established previously to substitute the RGB values of the points in the selected area, which proves that except for dealing with traditional 3D space relationship, the research also has the development potential for higher dimensional space design. And because each point in a point cloud model is independent and is not affected by the surrounding points, the model is different from the multiple independent mesh objects that use a Boolean operation to combine them into one object, which requires considerable calculations, memory, and high time cost. In this regard, the point cloud model requires the attachment of the depth image of the object to be combined with the original model in the most suitable projection image, and it used to module in OpenCV to extract the alpha channel values in the area. As a result, the value will be directly projected onto the corresponding point in the 3D point cloud model. The depth image can also be used to extend or copy the existing points to produce smooth curves and surfaces and other effects. Thus, the design can meet the functional requirements and demonstrated modeling aesthetic accordingly. And in the end, we used a cube sculpture process to illustrate that the point cloud can get rid of physical constraints in Rhino. All the points can quickly selected in the irregular range without the mousebox selection, and any two-dimensional image materials can be combined with three-dimensional point clouds as application methods in 3D CAD and others to verify our research results. Thank you for your attention.